Hi guys, this is Nicole discussing motivation for merge sort. So why do we care about sorting as computer scientists? Well, in life, we often have to deal with sequential information, lists of information where not only does the literal content of the list matter, the literal names in this list of some of my lovely recitation students, but we also care about the order of the elements in the sequence. Okay, it doesn't that sequence could be list of names, list of dates, list of numbers, and that's what our array data structure does for us, right? We store the elements in the array, but also that sense of order. That's kind of like another piece of information being stored, because we have the position of each of the elements in the array also stored. So we want to sort, these lists, and sure, we could manually sort the names from A to Z. We could manually sort the dates from oldest to newest. And we could manually sort the numbers from least to greatest. But a very natural question pops up. How can we get a computer to automate this task? How can we get a computer to sort the information from least to greatest or greatest to least for us? And the answer is in sorting algorithms. So previously, we already discussed two other sorting algorithms in this class. So for selection sort, we noted that the best and worst case time complexities are both O of n squared. It doesn't matter if you input into the selection sort algorithm an array that's already perfectly sorted, right? So it doesn't matter if we input an array that's already perfectly sorted, in this case that I just wrote from least to greatest, or if you gave the method, inputted into the method, an array that was in the reverse of the desired order. Say instead of 1, 2, 3, 3, 2, 1. It doesn't matter. For any element arrangement combination for arrays of the same size, the number of operations performed in order to sort the array will be the same, will be constant, okay? And hence, a best case of O of n squared and a worst case of O of n squared for selection sorts time complexity. You could also think of it as not having a best case or a worst case, just the only case. Okay, and selection sort was our simplest and most naive sorting algorithm, right? For many of us, the most intuitive. So, if you do not feel in your bones that selection sort makes sense, I highly recommend that you review Professor Centeno's learning objective videos on selection sort, right? At introcs.cs.rutgers.edu. Okay, and for insertion sort, we noted that the best case time complexity was O of n. Okay, that was our best case, and the worst case was the same as selection sort O of n squared. So in this way, insertion sort is an improvement to selection sort, right? An improvement. Okay. In the sense that for arrays that are already perfectly sorted or nearly perfectly sorted, completing the sorting, the insertion sort process only takes a time complexity of O of n versus O of n squared. Okay, and keep in mind the desirability of the time complexities. So, there's many different notations to denote time complexities. For us, we use, there's theta, there's tau, but for us, we'll focus on big O notation. And if you recall, least desirable, really the time it takes to do an algorithm blowing up, like O of n factorial, O of n cubed, O of n squared. Well, it starts to get desirable when we have like our O of n log n, right? O of n, O of log n, O of 1, constant time. So these are our more desirable time complexities, right? Okay, so the question becomes, is there an algorithm that consistently has a more desirable time complexity for the best case and the worst case for the algorithm? Maybe not a time complexity as good as, O of n, right? In the case of the best case for insertion sort, but just a time complexity better than O of n squared. Just better than O of n squared, such as, O and log n for both the best and the worst case scenario, right? And does such an algorithm exist? Does such an algorithm exist? Well, the answer is yes. And that sorting algorithm is called merge sort, which we'll be discussing in the following videos.